Hello! Today we will speak about nuclear technology in material science. Radiation material science is a section of radiation physics. Studies materials that are resistant to radiation or those properties can be modified, if necessary, by means of dose irradiation. Such materials are widely used in modern nuclear technology, including manufacture of various structural units and working parts of nuclear and thermonuclear reactors. When considering the behavior of materials under the influence of radiation, attention is paid to their ability and withstand the effluent of radiation while maintaining or improving their original properties. The interaction of radiation with the material is accompanied by a number of radiation effects, which as a consequences affect the mechanical properties. Let's speak about ionizing radiation and how does it appear. Radioactivity is the ability of unstable nuclei to transform into other nuclei, and the process of transformation is accompanied by the emission of various particles. After the discovery of radioactive elements, the study of the physical nature of the radiation began. How did Röntgen discover X-ray? Röntgen worked later in his laboratory. When he left, he put off the lamp and suddenly in the darkness he saw a slight greenish glow. The substance in jar standing off the table is glowing. Röntgen saw that he had forgotten to turn off one device, an electronic vacuum tube. He turned off the tube. The glow disappeared. Turn it on again appeared. The scientists came to the conclusion that some unknown radiation was emanation from the device. Röntgen called it X-ray. During the research, Röntgen noticed that the new rays were able to penetrate surface. It found that almost all objects became transparent in the rays: wood, fabric, and glass. In one of these experiments, he placed a box with a set of weights under the rays. The scientist's hands fell under the beam of rays. It's his own amazement Röntgen saw the bones on his hand moving. Bone tissue, like metal, turned out to be impermeable to the rays. Let's consider an experiment that allow us to detect the complex composition of radioactive radiation. Note that be set up and placed in a vacuum. A narrow channel is made in a piece of lead. The radium preparation is placed at the bottom of the channel. Let's place a photographic plate opposite the channel. After development, there was a dark spot on the photograph plate, which is located exactly opposite the channel. Let's create a strong magnetic field. The induction lines in which are perpendicular to the beam. The magnetic fields acts on the radiation coming out of the channel. The beam splits into three beams. Two of them deflect of opposite direction, which indicates that this radiation have electric charge of opposite signs. The negative elements of the radiation was deflected by the magnetic field much more strongly than the positive one. The third beam is not deflected by the magnetic field at all. The positively charged component is called alpha rays. The negatively charged one is called beta rays, and the neutral one is called gamma rays. Alpha radiation is a stream of positively charged particles, helium nuclei. which moves at a high speed. Alpha rays are formed during the radioactive decay of nuclei of elements with high atomic number and during nuclear reaction and transformation. The range of alpha particles is a substance depends on their energy and the nature of the substance in which they move. Since alpha particles are massive and have relatively high energy, their path in a substance is straight. They cause a strongly pronounced ionizing effect. All the energy is transferred to their body's cells, causing great harm to it. Beta radiation is a flux of beta particles consisting of electrons, negatively charged particles, and positrons, positively charged particles, emitted by atomic nuclei during their beta decay. Beta particles carry one elementary electric charge and have rates depending on their radiation energy. The energy of beta particles fluctuates significantly. This is explained by the fact that during each beta decay of radioactive nuclei, the energy generated is distributed between the daughter nuclei, beta particles, and neutrons in different proportion. And the energy of beta particles can fluctuate from 0 to some maximum value. The ionizing ability of beta particles is significantly low than that of alpha particles. The degree of ionization depends on their speed. The lower the speed, the greater the ionizing. Gamma radiation is a radiation of nuclear origin. It is emitted by nuclei of atoms during alpha and beta decay of natural artificial radionuclides. It's cases where the daughter nucleus contain excess energy not captured by corpuscular radiation, alpha and beta particles. The excess energy is instantly emitted as gamma quanta. That is, gamma radiation is a flow of electromagnetic waves, quanta, emitted during radioactive decay when the energy state of nuclear changed. In addition, gamma quanta are formed during the annihilation of the positron and an electron. In terms of properties, gamma radiation is close to X-ray radiation, but has greater speed and energy. Since gamma rays have no charge, they do not deviate in electric and magnetic fields, spreading rectilinearly and uniformly in all directions from the source. Neutron radiation is a radiation consisting of neutrons, that is, neutral particles. Neutrons are formed in nuclear reaction. Neutron radiation is indirectly ionizable. The formation of ions occurs not under the action of neutrons themselves, but under the action of secondary heavy charged particles or gamma quanta, to which neutrons transfer their energy. Neutron radiation is extremely dangerous due to its high penetrating ability. In addition, neutron can cause induced radioactivity, converting atoms to stable elements into their radioactive isotopes. One of the main properties of radioactive radiation is the ability to penetrate substance. Neutrons, gamma rays, alpha or beta particles have different penetrating abilities. When a person is exposed to external radiation, alpha particles are completely retained by the surface layer of the skin, so they do not pose a danger until radioactive substance emitting alpha particles. enter the body through the open wound with food or with air, then can become extremely dangerous. Penetration is low, can be stopped by a sheet of paper or human skin. Beta particles cannot penetrate into the human body more than a few millimeters. Penetration is medium, can be stopped with the aluminum sheet. The penetrating power of gamma radiation, which propagates at the speed of light, is very high. It can be stopped only by thick lead or concrete step. Gamma quant cause irradiation in the whole body. Neutrons have no charge and can penetrate many materials, then have a high penetration power. To slow down or stop neutrons, substances with a higher hydrogen content are required, such as water or paraffin. What happens when charged particles go through solids? The process of passing ionizing radiation carrying a large amount of energy through matter leaves its mark to be form of change in the structure on the matter. When passing through a substance, particles interact with the atoms of which it consists. That is, electrons and atomic nuclei, or nucleus of nuclei. The nature of the interaction of radiation with a substance depends on their types, energy, flux density, and also on the physical and chemical properties of the substance itself. The passage of an alpha and beta particles through a substance is accompanied by three types of interaction: ionization of atoms and molecules, excitation of atoms and molecules, dissociation of molecules for alpha particles, and deceleration of the electrons in the Coulomb fields of the nucleus for the beta particles. Interaction of gamma quantum with matter, photoelectric effect, scattering of gamma quantum, formation of electron pairs. Interaction of neutron with matter is elastic scattering, inelastic scattering, neutron emission, radiation capture, nuclear reactions, and nuclear fission. Particle accelerators. Accelerators are devices for obtaining directed flows, beams, of charged particles, electrons, ions, protons. In the case, the particles are given a certain speed. This energy is used in technological process and scientific research. The most important technical indicator of the accelerator is the energy of charged particles in a beam as the accelerator output. The accelerator consists of a chain of metal tubes placed one after another on one axis, placed in a vacuum chamber. In the gaps between the tube, a high-frequency longitudinal electric field is created, which accelerates the charged particles. These gaps are called the accelerating gaps. There is no energy field inside the tubes. The particles have passed through tubes, do not change their speed, and particles in the linear accelerator move in a bunch. When the accelerating field acts in the gap between the tube, the particles move in the gap. To achieve high energies, it is necessary to build a long linear accelerator. The largest linear accelerator was built in Stanford, USA. It was about 3 kilometers long and accelerated both electrons and positrons to a high energy. Ion implantation or ion doping is a technology mainly used in producing donor or acceptor impurities into the silicon crystal lattice. The doping impurities are pre-ionized, and the wafers themselves may be at room temperature or slightly elevated temperature, insufficient to activate the process of diffusion or distribution of their impurity. The ions are directed to the substrate on which a protective silicon mask can be performed. The protective mask is thick, enough for the impurity ions to get stuck in it. So the ions flow directed perpendicular to the substrate. The dimension of doped region will exactly match of the dimension of the window in the oxide. When entering the silicon, the ions experience multiple collision with the nuclei and interaction with the electrons of the silicon atoms. This leads to the gradual slowing down of the ions until they stop completely. Ion implantation has a number of advantages over traditional doping method. Here some of them. More accurate and reproducible dosing of the implanted impurity due to control of the ion beam current and irradiation time. Obtain high accuracy of impurity depth. Carry out the process at low temperatures. Allow the substrates with any allowing impurities in various. Carry out the process quickly in a few minutes. To produce materials with improved properties, metals are increasingly exposed to charged particle beams, plasma flows, and laser radiation. Ion implantation is one such method which allows changing the elemental composition, microstructure, and morphology of surface layer that determine such properties of materials as wear-resistant, corrosion-resistant, and others. In addition, this technology can be used to create parts and produce specific surface properties. For example, when zirconium is ion doped with titanium, a barrier layer is formed that prevents hydrogen penetration, which can be used to increase the service life and improve the safety of nuclear fuel elements. The video demonstrates processing of ion implantation in diamond. Another application of radioisotopes is nuclear physics analysis. Then, at the injunction of nuclear physics, radiochemistry, and other disciplines, a new direction emerging: nuclear physics methods of analysis, NPA. In general, nuclear physics methods analysis is are based on irradiation of the study samples with flow exciting radiation, neutron, charged particles, and gamma quantum, and then recording the results secondary radiation of the sample atoms. NPA belongs to the class of methods of elemental analysis of matter, the result of which is a quantitative determination of the content of the desired elements in the sample regardless of its chemical bonds. Let's consider another very common type of NFA, X-ray emission analysis, XEA. When irradiated with ionizing particles, each element present in the sample induced characteristics X-ray radiation. By the position of the certain proton energy in the general spectrum, each element can be identified, and by the intensities of protons of their energies. The concentration of elements can be found. This is the principle of XEA. X-ray emission analysis is a heavy charged particles. Excitation has only been used since 1970s. However, the method has already gained recognition and is rapidly being introduced into industry, medicine, and environmental protection. Other examples were industrial use of proton of particle excited REA may be economically feasible, including monitor of metallic impurities in a thin coating or copper wire and monitoring of surface contamination of magnetic film. There is no doubt that REA, with excitation of protons and other heavy chain charge particles obtained in acceleration, will develop an accelerated pace compared to other analytic methods carried out in accelerators. Thank you for your kindly attention.